This is part 2 in the video series on different factors that influence muscle tension. Today we're going to be talking about contraction duration, how long a muscle contraction lasts. Specifically, we'll be looking at how long maximum effort contractions last. Okay, first thing to understand is that your muscles do not operate on an on-off switch. You don't just get 0% or 100% tension. Rather, your brain can control pretty precisely how much tension your muscles generate. Now, we need to understand that process, so we're going to go back and look at some anatomy. In a muscle, there are many thousands of muscle fibers. Those fibers are activated by nervous system cells called motor neurons. Each fiber is innervated by just one neuron, but a neuron innervates multiple muscle fibers, maybe even 1,000 or more in your larger muscle groups. Each motor neuron, together with all the fibers that it activates, is called a motor unit. So one of the ways that your brain controls muscle tension is by controlling how many muscle fibers get activated. This is done through what we call motor unit recruitment. The more motor units that your brain sends a signal to, or recruits, the more muscle fibers get activated and the more tension you get. The other way that the brain controls muscle tension is through rate coding. What we have in a motor unit is a stimulus from the motor neuron causing a response in the muscle fibers. Now, rate coding is the process of controlling the response in the muscle fibers by controlling the rate of the signals through the motor neuron. Let me explain some more. So let's say we're looking at just one muscle fiber, and the tension is at 0. Now you get one nerve signal to that fiber. All it does is create a small twitch. It's a quick jump in tension and then it relaxes. Now this is only going to last at the very most 0.2 seconds if it's a slow twitch fiber. Now the thing to understand is you don't have any control over this twitch. Once you send that signal, it just happens. You can't control it at all. So when you perform a movement, first of all, you need some control, and you also need it to be able to last as long as you want it to last. So you don't just send one signal to a muscle fiber. What you do is you send a whole bunch of signals in a row. What that does is, before this twitch relaxes all the way, you get another twitch, and it adds on. You get another twitch, it adds on, another twitch, it adds on. So the tension keeps building up until the point where the twitches and the relaxation balance each other out, and then you just have somewhat steady tension. So this is called twitch summation, and up here this is called tetanus. Now the frequency of these nerve signals controls how much twitch summation you get and how much tension you get while you're in tetanus. So you can control the tension in all the muscle fibers in a motor unit by controlling the frequency of the nerve signals going to that motor unit. That's rate coding. Here's a better picture. The graph shows tension in a muscle fiber. The pink arrows below the graph represent nerve signals. So in number 1, we see one nerve signal and one twitch. In number 2, we have a few signals, and they're close enough together to cause some twitch summation in the fiber. In number 3, we have a higher frequency of signals. This causes twitch summation and the muscle fiber reaches tetanus. Then in number 4, we have a high frequency of nerve signals. This produces fast twitch summation and tetanus in the muscle fiber. This is meant to represent the highest possible tension the fiber can produce. So your brain can control how many muscle fibers are activated using motor unit recruitment, and it can control how much tension is produced in those muscle fibers by using rate coding. Now let's get back to this issue of time. Something I need to cover is that, remember, a motor unit is the motor neuron and all the fibers that it activates. Now all the fibers within a motor unit are the same twitch speed. So you have slow twitch motor units and fast twitch motor units. Alright, now when you go to perform a movement, motor unit recruitment occurs based on what we call the size principle. Your brain starts by recruiting the slow, weak motor units, and then it progresses to recruiting the fast, strong motor units as the movement demands. Now, that's a necessary thing. That's what allows you to move precisely with control, to move with an appropriate amount of force. So, when you go to feed yourself, you can bring the food to your mouth instead of smacking yourself in the face. But what we learn from this is that motor unit recruitment is a process. So, when you want to do something that's maximum effort, like a jump or sprinting or throwing, you can't just jump right to maximum motor unit recruitment. There's a process of going through the slower, weaker motor units, getting to the faster, stronger ones. That process takes time. So activating muscle fibers takes some time. Also, when we looked at rate coding, we saw that within each muscle fiber, producing maximum tension takes time. Look again at this graph and you see that that twitch summation is not instantaneous. You don't get maximum tension right away. There's a process to getting there. Now we want to look at muscle tension during a maximum effort contraction. And you can see the impact of motor unit recruitment and rate coding on muscle tension when you look at isometric force curves. Isometric force curves show muscle tension during a maximum effort isometric contraction with the limb locked into a machine. So now we're looking at tension in a whole muscle. We have tension versus time. Now again, your tension cannot just shoot up right to 100% instantly. That's not the way it works. It takes some time to get up there. So instead what we see is a curve, where you go up on a slope and then you level off. This is your isometric force curve. Now different people have a little bit different force curves. For example, a weaker person would have a lower force curve. A more explosive person would have a curve that goes up faster on the left. But the main point here is, no matter who you are, it takes some time to get up to your maximum tension. From here to here, that much time. Now, how much is that? Well, it's going to vary between different people. I'm not going to say that I know the average or anything, but I'm going to say that this is probably at least half a second for the vast majority of people. Now, some of you may be thinking, well, half a second's not very long. Does that really even matter? Well, yeah, it matters a lot. Because in the world of maximum effort muscle contractions, half a second is a really long time. In all high-speed movements or high-speed exercises, the muscle contractions that are used are much quicker than 0.5 seconds. For example, in top-speed sprinting and foot contact might last about 1/10 of a second or a little longer depending how fast you are. So that's how much time you have to produce force. Now in 1/10 of a second, you can only get up to about right there on your curve. So on this curve, that's what, like halfway up? Team sports, your acceleration, your cutting, your shuffling, you're going to have a little bit more time. Okay, so you get a little bit higher up your curve. Single leg jumping, maybe around 0.2 seconds. Here, a little bit higher up the curve. Two-leg jumping. Well, there's a lot of variety in two-leg jumping. As far as what you can use in sports, you're looking at probably a quarter second, maybe 0.3 at the most. Okay, so maybe you're out here. So all of these explosive movements are too fast in order to generate your maximum tension. So now we know when we look at different movements and exercises that more muscle tension can be produced if the period of maximum effort lasts longer, up to a point at least. Now there's a danger here of saying, oh, well, maybe I should make my movements last longer so I can generate more tension. Now that's not accurate. Let's say I'm lifting my arm. If I lift it fast, I'm going to generate a lot more tension than if I lift it slow. Because when I lift it fast, I have the maximum effort. Remember, we have to think of these things in context of maximum effort. So you don't get more muscle tension by intentionally making a movement last longer. You get more muscle tension when the conditions of an exercise force the movement to last longer. Now, what type of characteristics of exercises force them to take longer? Two things. One is weak biomechanical positions. Now, I'm not going to get really into this. I think I'll do a separate video on this. But basically, the more flexed you are, the weaker the position is. So the top of a pull-up is weak. The bottom of a bench press is weak. The bottom of a squat is weak. All right, those are weak biomechanical positions. When you get into those positions in an exercise, it takes a lot of tension to move out of those positions, and that slows the exercise down. The second thing that makes movements last longer is more resistance. Now this is pretty obvious. I can do a body squat faster than I can do a squat with a bunch of weight on my back. More resistance requires more force requires more time, so the movement lasts longer. Now, this is pretty logical to most people. I get more muscle tension when I lift heavier weight. But you got to realize that's only up to a point. Remember, you can get to your maximum tension in under a second. So once a movement is that long, making it longer won't necessarily give you more tension, it'll just make it last longer. So let's say, I would guess probably at about 70% of your max squat, you're generating just as much tension as you do at 100% of your max squat. The difference is that you're just generating it for a longer period of time with the heavier weight. Okay, so let's do some application. Remember, we're talking about the glute muscle. And in part one, we looked at movements that involved maximum effort and lengthened the glutes. Now, if we throw in the factor of how long the muscle contraction lasts, sprinting and jumping are now no longer candidates for being the movements that produce the most glute tension because they do not last long enough. Still in contention, we have deadlift and snatches and cleans from the floor and squats and lunges. And you'll notice these use weak biomechanical positions and they use resistance. Now we also mentioned squat jumps and lunge jumps. Now these movements are interesting because they are body weight movements. There's no extra resistance. They are full effort and explosive. However, because they use these weak biomechanical positions, they still take fairly long. You can still generate quite a bit of tension during a squat jump or a lunge jump. So we're going to leave those movements in as candidates for producing a lot of glute tension. In fact, in one of the factors that we're going to discuss that influences muscle tension, squat jumps and lunge jumps actually have an advantage over your weighted squats and your weighted lunges. Now that factor where those faster movements have an advantage is contraction velocity. That's what we're going to talk about in part 3. Stay tuned.